Gosh. All right. So Isaac, how confident are you that it's number 9? You're still looking?
No, it was number 7.
Number 7, okay. All right, so we're gonna go through number 7 and then we'll do number 36. What page was 7 on? 183. So just a friendly reminder, because I know that some of you get tempted. I am very, very happy and willing to and eager to grade homework from you every day if you need that. You should be doing homework every day, not waiting until I go over it and then thinking that that's enough, okay? I know that I don't check it because I'm going through the standards, but you need to make sure you're doing it every day so that you can be informed and have a conversation with us as we go through problems, as opposed to just like being a passive physicist. Passive physicists don't learn well. Let me just put it that way. So is this the one, the person lifts a 4.5 kilogram cement block? Is that the one you're looking at? And then he walks? Determine the work done? Okay. So in the beginning, here's the block. It's on the ground, and then he lifts it up. So in doing that, or she, I guess I don't know, the person lifts the block up. Do they do work when they're lifting the block up or no? Yeah? Yeah? Tell me about the applied force. Right? Is this making sense to you all? Do you have to write the net force out every time? No, I don't really care if you do or not. I just want you to know where it's coming from. So when I do it, I'm going to write it out. So my free body diagram shows that I've got an applied force and a gravitational force. If I'm lifting it up at a constant speed, or we're going to approximate it to be constant speed, then the applied force is going to be the mass times the acceleration due to gravity. So that's going to be, what was that, 4.5 kilograms? Go ahead.
If it's kilograms, you don't have to convert it.
No, I feel like the conversion from the stairs lab totally blew everybody's minds and like totally confused all of physics. The only reason we had to do that is because we live in America. Okay? The only reason we had to do that is because when you talk about the force of gravity pulling you down, we always talk about it in terms of what units? Our weight. In what units? In pounds, right? We always talk about it in terms of pounds. Nobody else talks about weight in terms of pounds, except the British, right? The British and us. Like, that's it. Nobody else in the world does, because everybody else in the world knows what they're doing. Okay? Everybody else in the world, when they talk about it, they talk about their mass in kilograms, and you can multiply that by 9.81, you're done. Okay? The only reason we had to do that crazy conversion was because we were trying to convert from pounds to newtons, because we know our weight in pounds, and you don't walk around telling people your weight in newtons. Like, that's not a thing. You could now, because you know how many newtons you weigh, right? Because you did the math. But this is how we do it to find FG. Go.
If you're not given the force, then you do that every time, the 9.8 times the weight.
So anytime you're lifting something straight up, right? Yeah, I understood. I was with you. Yeah. But yes, anytime you're lifting something straight up, because we assume that we're lifting it at a constant speed. So assuming we're lifting it at a constant speed, then these two forces have to be equal. And so then, yeah. Does that make sense? Yeah. How are we doing? Are we okay? Yeah? Okay. So 4.5 times 9.8 gives me some number. Anybody got it? What is it? 44.1? 44.1 what? Newtons? Yep. Okay, so that's the amount of force that we have to apply. The person is lifting it over a distance of 1.2 meters. So that means that the work done as we lift it up is going to be 44.1 newtons times 1.2 meters, which gives me a total amount of work of something.
52.92.
Oops. $52.92 joules. Okay, so that's the first half. Then it says that the person holds on to the block and carries it a distance like this. Is the person applying a force while they carry the block? For sure, because if they didn't apply that force up, then where would the block go? Ouch, right? That would be bad. So they're applying a force up. Are they doing work? Why not?
No, this way. Yeah, parallel.
Okay, so if we draw that picture, I'm just going to go ahead and draw that picture just to make sure we're all on the same page. So here it is. So we got a force going down, force of gravity. Got the force applied going up. The displacement is this direction. It was how much? 3 meters? 7.3 meters. They walked a long way. Okay, but because the applied force and the gravitational force are perpendicular or not parallel, there is no part of this force that's going in this direction, right? No part of this force is going in this direction, therefore there's no work done, okay? So there's no work done here. I don't know why this is not working. That's funny. No work done there, so the answer is just the 52.5 or 9592. Is that okay?
Will a lot of the problems be like mountain quiz, or will they be like the ones that we have to like use the shoe?
So you will not have to do, let me back up. I only am assessing this standard. So that means that you're not going to have to break things into components. You're not going to have to convert things. Not going to have to use kinematics. Does that make sense? Yeah. All right. I did want to look at that other problem too. So everybody will want to write this one down because this one I don't think we really understand yet. So this is on page 185, number 36. Have you guys read this problem yet? Have you looked at it?
Yeah.
Yeah. Does anybody need a minute to look at it again?
It's like the kilograms per.
It's weird, right?
We haven't done that yet.
Well, we kind of have. What I want you to do right now is I want you to read the problem. Again, number 36, it's about Niagara Falls. And I would like you to write down your givens. Because when you look at a problem and you don't know what to do, the first thing to do is to write down your givens. So go ahead and do that.
That's the mass. That's like one, two.
Look at your units. The units tell you everything.
That's the, okay. The speed.
What is okay?
What is that?
What is
Per second. What is that?
It's the rate of what?
Mass 5.
Yeah, but then height.
Mass per
Mass per second.
Yeah.
Displacement.
Maybe 25%. Wait, this is work. Let's just work this.
Power is what?
Yeah, that's what I meant.
But
It's really nice, just by the force.
He cares about
Times that.
and make sure
Every that would
no. Unless you walk away from me.
All right. So So let's take a moment to talk about what's going on. What's the situation here? What's going on? Emma, what do you see?
Forgiven.
Yeah,
Well, the distance is 50 meters,
for sure.
and then we're looking for power units.
Mm-hmm.
And the rate, well, the rate is 1.2 times 10 to the 6 kilograms per second. I don't know if you would say that's again.
Yeah, so we need to figure out what that is, right? That's the kind of scary one because it's like, I don't know what this thing is. But if we look at the units, that's going to tell us what we need to know, right? Yeah. So the rate is 1.2 times 10 to the 6 kilograms per second. What's kilogram measuring?
Mass.
The mass. So that means 1.2 times 10 to the 6, that mass, every second, that amount of water is going over the edge.
It's going over the edge, but the acceleration of the water would be negative 9.8.
Oh, okay. So you got the acceleration of the water as it's falling is 9.8. I'm going to leave the negative off right now just because we're really just talking about the amount, right? Yeah. Okay. What do we do with all this stuff? Just blindly? Or is there a reason that you decided to do that? Tell me about your reasoning, Leanne.
Because work is distance times force. Distance times force. And force is the mass times the acceleration.
Okay.
And so we're given the acceleration and
Okay.
the mass and the distance. And then that's all going to be divided by time, and the time is already on the bottom.
Right. So the scary thing here is that you've got time over here already. Are you with me there? It's a little bit weird that you've got time over there already. But I'm going to do kind of what Leanne was saying and just kind of put it all together. So power is work times or work over time, which means it's force times distance over time, right? Which still doesn't look perfect because we don't have a force. But that's equal to mass times acceleration times distance divided by time. And so all I'm doing is just pushing those equations together, making them try to sit nicely together. Okay. And then, like you just said, we've got distance, we've got acceleration, and then we can look at this thing as one number, the mass over time. That's what this is. Whoa, come on. That's what that one is. Okay. The thing you have to be careful about is just blindly multiplying numbers together, because in this case it works, right? Not every time does it work that way. So you need to make sure that you're looking at units. So if you're like, I really don't know, we can look at the units here. So this is kilograms per second times meters per second squared times meters. We could write that out. Well, that's gross. Kilogram, meter per, let's see, how do I want to do that? Meter per second. I don't know if I want to write it out that way. I'm going to pull that 1 second down to the bottom. That's your Newton. A Newton meter is a joule. And a joule per second is, what is that one called?
A watt.
A watt. Yeah. Is that okay? Yeah. It's not too bad. It's doable if you think about it. You just got to think. You got to take it one step at a time. Yeah, but you got it. You got it. All right. We're going to do a lab. So I'm going to kind of get you started on this lab. It's a new lab for me in that I've never done this with my physics classes before.